The last topic we have for blood right now is going to be the concept of hemostasis. Blood clotting, vascular repair all falls under hemostasis. Last time we talked about production of red blood cells and white blood cells. We had mentioned a little bit about platelets up to this point, but this is where the platelets are going to shine, their role in blood clotting and vascular repair. We will see platelets contain overlapping filaments, very similar to what we saw in muscle tissue. So we will see the formation of a platelet plug, a loose collection of sticky platelets that's going to attempt to plug a hole in a blood vessel that's been damaged. These overlapping filaments, just like we see with muscular contraction, it will take this loose arrangement of platelets and make it condense upon itself, increasing its density and forming a much tighter seal wherever the damage has to occur. Now remember, platelets aren't actual cells, they're cellular fragments. Megakaryocytes, these large blood cells, we see fragments chip off. Those are your platelets. So these in no way, shape, or form are going to be considered a cell, and it's because of the platelets that we use the term formed elements instead of simply blood cells. The megakaryocytes are going to remain in the bone marrow and sending off these platelet fragments into circulation. We saw erythropoietin driving red blood cell production. We saw various chemical messengers like our cytokines and our interferons and our lymphokines driving white blood cell production and migration. Here we have another hormone, thrombopoietin. Now, for the most part, we're going to want to see a nice steady level of platelet production in the blood. It'll follow that negative feedback loop somewhat in the same similar pattern that we see any other negative feedback loop. However, we will see times of increased thrombopoietin in times of extensive vascular damage. So if we are talking about a small cut, for example, to simplify this down to a point, you should have adequate platelet counts circulating throughout the blood to handle small vascular damage. If that continues on long periods of time, multiple small traumas or smaller number of larger traumas, then we will see thrombopoietin kick in and increase that platelet circulation because you're going to be consuming them more in the vascular repair of those multiple sites. This thrombopoietin is going to be produced in the liver, and it's going to increase activity of these megakaryocytes. Remember, the platelets are not cells. The megakaryocytes chip off these fragments. So thrombopoietin increases activity in the bone marrow of these megakaryocytes to increase their platelet production. We see three overall phases in hemostasis. Hemo referring to blood, stasis meaning to stop. First off is a vascular spasm, vasoconstriction. That's when we take those small arterioles and we make them smaller. You're going to see a relationship throughout our cardiovascular unit where we talk about pressure and resistance. If we take a blood vessel that's this big and we constrict it so now that it's that big, we increase the pressure inside that blood vessel, but we also increase the resistance to flow. Increasing the resistance to flow is going to limit how much blood actually gets to the damaged site. We're in a blood vessel here, blood's flowing in this direction, the damage is downstream, we vasoconstrict here and we limit the amount of blood that ever gets to the damaged site. Now there are going to be times when we'll talk about vasoconstriction that is so strong that it completely eliminates blood flow. You'll get to that once you do urinary function. When you go into a state of fight or flight with that sympathetic nervous system activating, you get such powerful vasoconstriction at the arterioles leading to the kidneys that you shut down the ability of the kidney to filter the blood, therefore you shut down urine production. So we slow down blood flow to limit the amount that ever gets to the damaged site. Now we can start repairing. The first step is going to be the formation of a platelet plug. After that occurs, then we go through blood coagulation, blood clotting. Now, it's important to realize that a lot of the agents that we're going to be discussing in the platelet plug and clotting activities are always in normal circulation, but you can consider them to be inactive. When blood is inside the lumen of a blood vessel, it's sealed off from any contents of that vessel, the structure, by that tunica intimum, that thin layer of epithelial tissue. That's the layer that comes in contact with blood through times of normal blood flow. However, if we get vascular damage here, obviously blood now is going to get exposed to some of those underlying structures. And the underlying structure of most significance is going to be collagen fibers. Now, on this simple drawing diagram, it's these purple lines that are supposed to indicate the collagen fibers. And of course, they're indicated down here, superficial to the muscular layer. But we also have some connective tissue right underneath that epithelial lining, which can also contain collagen fibers. But regardless, we are going to be considering the exposure of blood to these newly unsurfaced collagen fibers to be the activating point to send us into a platelet plug formation and ultimate blood clotting. When platelets interact with those exposed collagen fibers, we see them secrete two chemicals. The first one is ADP. This is the same ADP you would have talked about when you mentioned energy production in the body. If we take an ATP molecule and we break it down, we get an ADP molecule. Same thing. Secretions of ADP from the platelets results in the platelets changing their surface characteristics. They become sticky. Here's a normal platelet, or a smooth outer surface. On the right are platelets that have become activated. Now, the closest thing I could describe these two in everyday occurrences would be those burrs that you find on plants. You go hiking through the gorge, you go through some brush, and you may wind up getting back in your car with these sticky burrs. Pockets of seeds, looks like they have Velcro hooks on them that grab onto your clothes, and it's a way of that plant to spreading its seed. Not only will it adhere to your clothes, or Velcro will adhere to other pieces of Velcro, if you get the surfaces of these platelets to take on that appearance, they will start sticking to each other. This is the activated form of those platelets. This is the sticky characteristic of those platelets. ADP drives that appearance change. We also see platelets secrete another chemical called thromboxane A2. Now, this is a reinforcement, because thromboxane A2 causes the platelets to produce even more ADP. This is an acceleratory process. You may have even heard some people describe blood clotting and platelet plug formation as a positive feedback phenomenon. It's not a positive feedback. We still only have one positive feedback in the body, that's the birthing process. But this is an acceleratory process. You have the platelets producing ATP and secreting it, making it become sticky. They also produce a chemical called thromboxane A2, which results in even more ADP getting secreted, accelerating that sticky nature of our platelets. You'll see ADP take on another role here before we're done as well. Up to this point, those increased sticky platelets can adhere to each other, but it doesn't help us at all unless that sticky mass of platelets can be adhered to the damaged vessel wall. Right? It's called a platelet plug. It's meant to plug the hole. We see another circulating protein that springs into action when collagen fibers are exposed. the von Willebrand factor. Von Willebrand factor is a protein that circulates normally in the blood without consequence. But when we see exposed collagen fibers, von Willebrand factor binds to the exposed collagen. Now the platelets have something to attach onto. The sticky platelets may not have been able to bind to the exposed collagen themselves, but now that the von Willebrand factor is present, they can adhere onto that von Willebrand factor. So the von Willebrand factor essentially acts as a bridge. You have the exposed collagen from the damaged blood vessel wall. You have the massive sticky platelets that have formed because of the secretions of ADP and thromboxane A2 in light of the collagen being exposed. And anchoring both of those together is going to be that protein of the von Willebrand factor. Now we get not just the platelet plug, but we get it in the right location, plugging the hole where the blood vessel damage happens to be. From there, remember, at this point, it's still a looser mass of platelets. This is where the actin and myosin filament complex inside those platelets take effect. A loose mass of sticky platelets adhered to that damaged blood vessel wall by the von Willebrand factor now condenses. And as it does, remember, it's anchored to the von Willebrand factor, so it's going to be pulled more so down into that damaged vessel, plugging the hole and forming a much tighter seal. Now, it's important to realize at this point, we only want the platelet plug doing its thing where the damage occurs. We don't want that mass of platelets spreading throughout the surface of normal, healthy blood vessel. In order to keep it from spreading, ADP has a secondary role. Remember, ADP was what triggered the platelets to become sticky. The platelets secreted ADP because of the exposed collagen. The ADP caused the platelets to become this sticky mass. ADP also stimulates normal epithelium to secrete two other chemicals, prostacyclin and nitric oxide. So the ADP, which may have been activating all of these platelets, moves in either direction, where we see no vessel damage, causing these epithelial cells to secrete nitric oxide and prostacyclin. Prostacyclin and nitric acid has the opposite effect on the platelets. And it keeps all of this platelet activation localized only to the site of blood vessel damage. You got this acceleratory cascade of events forming the platelet plug. And as we move away from the damage, that entire process is being inhibited by prostacyclin and nitric acid. So now we got our platelet plug formed. It's stuffed into the hole where the vessel damage happens to be. Now we want to go through blood coagulation so we can go through the process of healing the vessel. We don't just want the vessel plugged. We want to go back and we want to fix the damage. Here we get into one of the proteins that helps characterize blood as a connective tissue as a whole, fibrinogen. Fibrinogen is going to be that soluble fibrous protein circulating in the plasma, fibrous component of blood. It's going to be converted into an insoluble fiber called fibrin. This insoluble fiber now forms a net, catching anything that's passing through. It's going to catch masses of red blood cells. It's going to form a clot in the area where the platelet plug had formed. So this diagram, I know the writing is a little small, but it'll be bigger in your notes. Across the top is what we've discussed so far. Those three blood vessels across the top illustrates the formation of the platelet plug. We got the exposed collagen on the left. We got the platelets forming in the second picture, plugging the hole. So as we move across the top of that diagram, those three blood vessels, we're in between the second and the third one now. Where we left off here is in between at the end of that second blood vessel. Now it's time for the coagulation. The exposed collagen that we originally saw kick off the process of formation of the platelet plug also starts the coagulation process. It causes platelets to secrete another chemical called platelet factor 3. Platelet factor 3 produced and secreted from the platelets. We see it in conjunction with another protein, thromboplastin, other blood elements like calcium, and clotting factors. Causes a prothrombin activator, which starts off the cascade to eventually form our insoluble fibrin net. We have prothrombin getting transformed into thrombin, which then synthesizes fibrinogen to transform into fibrin. Now, when we say clotting factors, here is our clotting cascade. This would have been at the very end here, fibrinogen to fibrin. On a more simple looking diagram, that's where we were. But you can see any number of other clotting factors, 8, 7, 10, 5. You've heard of conditions like hemophilia. Very often hemophiliacs have a deficit in one or more of these clotting factors, giving them any range of inability to clot blood. But what you will notice also is that we have two pathways. We have an extrinsic, beginning over here, and an intrinsic on the upper left. Now, all roads lead to the same place here. Regardless of where we start this clotting cascade, we still wind up transforming fibrinogen into fibrin to form that insoluble net for blood clotting. However, what kicks off each of these pathways is going to differ. Intrinsic, based on the name, should help you imply that intrinsic pathways are going to use because of internal vascular damage. Extrinsic pathways are going to be kicked off by external vascular damage. What are some examples of each? Blunt force trauma to the side of your leg, rupturing blood vessels. That's extrinsic. A laceration is extrinsic. Intrinsic may be damage secondary to an aneurysm. You basically damage the blood vessel from two different perspectives, which winds up kicking off the clotting cascade from two different launching points. We do see differences, chemical differences as well as practical differences, if you will, depending on which type of vascular damage we exhibit. We pointed out earlier that we see a lot less clotting factors involved in our extrinsic. Only uses clotting factor 7, 8, 9, 10, 5 is not even on the list. They're going to be more so involved in the intrinsic. Intrinsic pathways tend to be slower. You will tend to see a much quicker clotting time with an external damage mechanism than you will by a ruptured aneurysm. Which is why it seems like we get a lot more vascular flow through those small capillaries that happen to be damaged with the brain capillaries that have ruptured, as opposed to something in the limbs caused by external trauma. And here would be a little bit of an impression of what that blood clot would wind up looking like. We see that insoluble fibrin net catching anything that happens to be flowing through at that point. Mostly red blood cells, of course, because that's going to be more prominent feature that we find in blood. So note the three different processes that we see with hemostasis: vascular constriction, platelet plug formation, and then coagulation. For the platelet plug, you should know that one in pretty good detail. What activates the platelets? What chemicals are involved? What chemicals keep that platelet plug from spreading over healthy blood vessels? For the coagulation, I would know the differences between the intrinsic and the extrinsic pathways. Fibrin going to fibrinogen, and also how that entire process fits into the timeline of the formation of the platelet plug. So that should clue up our discussion of blood. However, we will still be talking about blood in many different contexts. Again, we can't go on talking about the cardiovascular system without referring to blood frequently. We can't talk about the respiratory system and blood gas transport without referring to the blood frequently. We won't even be able to go through renal and the filtration of the blood without referring to blood composition frequently. So these topics sort of come back over and over and over again. That wasn't even mentioning, again, immune function. So you'll see this spill over into other topics, which is what A&P2 happens to do. It's one continuous story, more so than you've been used to in A&P1, where we can talk about integument, and it really has very little to do with skeleton. And that has very little to do with nervous. A lot of the topics we're going to cover this semester are going to be intertwined for an entire semester. If you have any questions, please let me know. Thank you.